So Mr. C is going skydiving, and here written in pencil are the given values of our situation. We know that his acceleration due to gravity in the y direction is negative 9.8 meters per second squared, that his y displacement is negative 1,000 because he's jumping from a plane 1,000 meters above the ground. We know that his x acceleration is 0. We also know that the plane is moving at a speed or a velocity of 350 miles per hour. And so we need to change this into meters per second in order to plug it into our equations to answer the questions. So 350 miles per hour is this many meters per hour, and 1 hour is equal to 3,600 seconds because there's 60 minutes in an hour and 60 seconds in a minute. And so his meters per second is 563,270,000 meters per 3,600 seconds, and simplified, that is 156.46 meters per second. So we plug this in here, and so the first value that we're able to find is the change in time because of the values that we have. And so we plugged in the y values into the displacement equals velocity initial times time plus 1/2 acceleration times squared. And so the y displacement, so negative 1,000 meters equals 1/2 negative 8 times time squared, and 1/2 times negative 9.8 is 4.9. So negative 1,000 divided by negative 4.9 equals the time squared. And then you need to square root both of those, and this gives you the change in time, which is 14.29 seconds. And so now that we have the change in time, we can plug that back into the same equation using the x values. So the x displacement, or change in position in the x direction, is change in time, which is 14.29 seconds, times the initial velocity, which is our meters per second that we found. And that is equal to 2,235.81 meters, and that's the displacement. And so we know that this is how far he would jump from the plane in order to make it in the landing zone. And so then it asks, if Mr. C jumps 5 seconds late, how far would he miss the landing zone by? And so if he jumps 5 seconds late, that adds 5 seconds on our change in time, and our new time is 19.29 seconds. And so if you plug this time into the same equation we used here down into this one, it's the same thing, the initial velocity times the change in time. And so if their new change in time, the displacement in the x direction is 3,018.11 meters. So that's how far he would travel jumping from the plane to the ground. And so since we know that the landing zone is 2,235.81 meters away, he would miss it by 786.3 because we subtract the distance of the landing zone minus the distance that he actually traveled. So he misses it by this much. And now we know that the forces acting on Mr. C are gravity, because his acceleration due to gravity is negative 9.8 meters per second squared. Drag is not acting on him in this situation, and there's no horizontal force acting on Mr. C because inertia is what causes him to move horizontally. So moving over to our velocity and acceleration vectors, in the x direction, his velocity is constant, and I marked that. And in the y direction, his velocity increases by negative 9.8 meters per second squared. And so I made sure to indicate that he traveled farther and farther with each second. Acceleration in the x direction, there is none. And so while the seconds continued to occur, there was no acceleration happening there, so there was no acceleration indicated. And his acceleration in the y direction was negative 9.8 meters per second squared. And so while his velocity was not constant, his acceleration was. So I marked that with constant vectors. And so there you have it. Mr. C needs to jump 2,231.81 meters from the plane to land in the landing zone. But if he jumps 5 seconds late, he'll miss the zone by 786.3 meters.